Hi all, Mrs. Vara here. I'm going to do examples 4 and 5 in section 9.4, the Lagrange remainder section. You're going to want to keep these formulas in mind while we're doing these problems, and I'll probably write them anyway, but I believe on Jason Nagato, I don't know how you say his name, website, examples 4 and 5 were not on there, so we'll look at those on here. So example 4 says determine the degree of a Maclaurin. So remember, when you see the word Maclaurin, it is always centered at 0. So determine the degree of a Maclaurin polynomial required for the error approximation of this function, e to the x, at x equals 1/2 to be less than 0.001. So if you think about that big long remainder formula, what we're looking for here is we're looking for the remainder to be less than or equal to 0.001. Okay, now if you think about the formula, going to put the formula up here for a minute. A large part of the formula is this, which is the maximum of the derivative of f at n plus 1, not at x, but at z. And remember, z is always a value between x and c. Okay, so I usually start these problems with this part, because once you figure out something about this part, the rest of this is not too bad to plug in. And that's actually how I started this one. So what I'm looking at right now is just the max of the absolute value of f of n plus 1 of z, absolute value. So for any derivative of e to the x, first derivative is e to the x, second derivative is e to the x, third derivative of is e to the x. So then I know that f of n of x is e to the x always. So I can say f of n plus 1 of z is also e to the x. So normally the next part we do is we look at the max. Z here is between 0, because we're centered at 0, and 2.5. I wrote 2.5, but I think it should be 0.5 because x is 1/2. So between 0 and 1/2. And I'm doing the max again. This is just kind of rewriting the formula here. So this is your basic formula with our z values filled in. And I'm going to say, hey, this is going to be e to the 1/2. So how did I make that big stretch from the max of all of this is going to be e to the 1/2? Actually, I don't want to make that big stretch. I am going to write that this is going to be the max when z is between 0 and 0.5 of, right? This is going to be e to the z, because we said the max, that the derivative is always e to the z. Now, if you think about the function e to the x, it's always increasing. I'm going to make that a z so it doesn't look like a 2. It's always increasing, right? It looks like this. And we're only concerned between 0 and 1/2. So where's the max going to be? It's going to be at 1/2. So we can go ahead and say this max is going to happen at e to the half or 0.5, right? For sure, we know that. So then this is the way these problems go, is lots of times they're functions that you kind of know something about, right? Like the sine and cosine problems, we know sine and cosine is always between 0 and 1. E to the x, we know it's always increasing. And we also know that e is roughly equal to 2.71, blah, 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 blah. So if we know that e is 2.7, then we know e is less than 3. So I could think, well, if e is less than 3, then the square root of e, which this is going to be less than the square root of 3. Which you could proceed ahead with this problem, but do you agree it's a lot nicer to say that e to the 1/2 is going to be less than 4 to the 1/2, because the square root of 4 is a nice number, right? The square root of 4 equals 2. So instead of using this, which is absolutely true, I'm just going to use the square root of 4 because it gives me a nice round number here. So this is a number that I'm going to use when I figure out my remainder or my error. Your remainder and your error are the same thing. So I am finding the remainder of n at 0.5, and I should put my absolute values around here. So this is going to be less than or equal to fn plus 1 of z all over n plus 1 factorial. And then I guess I'll just write the formula out here. X minus c to the n plus 1. I'm afraid I'm going to run out of room here. So all of this for our problem is the max of e to the z, right? All over n plus 1 factorial. We don't know that, right? That's what we're trying to find, the degree. And x minus c is just going to be 0.5 to the n plus 1. Now, if you think about this, what did we just say is true about all of this? We said it's going to be less than, or all of this is equal to 2. So remember, we're thinking less than here. So I can go ahead and say, well, I'm going to rewrite this. And this is the less than or equal to that I'm carrying over here. So I'm going to move it over here. I'm going to rewrite this as 2. And then I have n plus 1 factorial 0.5 to the n plus 1. Okay, so hopefully that makes sense. And then remember, this is our n of 0.5. Okay, so what they said was we want your error to be 0.001. So what I'm really looking at here is this right here is going to be 0.001 is less than or equal to all of this. Okay, I can do some algebra on this, some simplifying. I hope we don't run out of room here. So I'm going to kind of work with this part right here. And I'm going to say, well, this is the same as 2 over n plus 1 factorial. And I'm going to write this as 1/2. You'll see why in a second. Okay, so now I have that. I'm going to say, well, 1 to any power is still just 1. So I'm going to say this is the same as 2 over n plus 1 factorial times 1. And down here, this would be 2 to the n plus 1 also. But remember, I can write that as 2 to the n times 2 to the 1. So I'm just trying to simplify this up again a little bit because I have to solve for n. So here I have a 2 and a 2 on the bottom. So what I'm left with is a 2 to the n on the bottom and an n factorial. So I'm going to say this is where I'm at now. 2 to the n plus 1 factorial less than 0.001. Now this is kind of a trial and error. So I want to find the n that makes this inequality true. And actually this can be less than or equal to because the formula is less than or equal to. So it's just a process of elimination. Start with 1. Start with n equals 1, see how close you are. you're not that close, but you'll see quickly the values here get close to that, and where this happens is when n equals 4. So the degree of the Maclaurin polynomial would be a 4th degree. When you have a 4th degree Maclaurin polynomial, your error bound will be less than 0.001. So I guess technically that is our answer. All right, so that was example 4. Kind of long, I realize, but I'm trying to go through these a little bit longer too, since you haven't had his videos are a little brief, I think. Okay, so this one in example 5, so we're determining the values of x. So both of these are asking for something different. So we're finding x. Notice they didn't give us an x value like they did up here. They did tell us it's a Maclaurin, so I know c equals 0. This is our function, cosine. That can be replaced by a Maclaurin polynomial if the error cannot exceed this. So again, that same error number. So now this is a function that we know something about. So we're going to start by writing that memorized Maclaurin polynomial for cosine of x. And we need to go to a 4th degree. So it's going to be 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. So we're only going to 4th degree. So now then, let's think about our max. So our max and our z is going to be greater than 0 because we're starting at a Maclaurin, and it's going to be less than x. Remember, we don't know x for this one. And f of n plus 1 will be f of 5. And remember, this is at z, some value between x and c. And we want to see, can we make some kind of statement about the 5th derivative of cosine? Well, if you think about when we're taking derivatives of cosine, derivative of cosine is negative sine. Derivative of negative sine is negative cosine, right? The derivatives are always, so I'm just going to do this part over on the side here. Derivatives are always plus or minus cosine of x or plus or minus sine of x. Okay, well, what do we know about cosine of x and sine of x, right? We know cosine of x is always between -1 and 1. And we know sine of x is always between -1 and 1. So another way to write this is to say the absolute value of cosine of x is less than 1, or the absolute value of sine of x is less than 1, right? That's kind of what absolute value is. So we're taking this -1 and making it an absolute value. Well, I'm actually absolute valuing the function. So we know this is true. So if you come back here, you know this 5th derivative is either going to be plus or minus cosine or plus or minus sine. It's going to be one of those. We actually don't even need to know what it is, because we know the absolute value of either one of those is going to be less than or equal to 1. So here is where I can figure out where that function is bounded. All right, so now let's look at our big remainder formula, and when we get to this part, we know at some point we can substitute this in. I'm still going to write it out. It helps to write these just to memorize it. So the remainder is less than or equal to the max of f of n plus 1 at z. So Rn plus 1 is 5 at z, absolute value, all over n plus 1 factorial. Our n is 4, so 4 plus 1 is 5 over 5 factorial, times x. We don't know x. C is 0. X minus c to the 5th, to the n plus 1. Now, what did we figure out? We said, well, all of this is going to be less than or equal to 1. So I can say all of this. I'm just going to replace this with a 1. So where this max is, I'm going to put a 1. 5 factorial, absolute value of x to the 5th. Now this is just like we did above. They're saying we want this to be less than or equal to, what do they want it to be less than or equal to? 0.001. So this is what I simplified my remainder down to. And they said, hey, your remainder cannot exceed 0.001. So we just need to solve this for x. This one's a little bit easier. So you could start here by multiplying both sides by absolute value of 5. I'm sorry, not absolute value of 5. 5 factorial. And that gets you this. And then I want to 5th root both sides here. So I get absolute value of x is less than or equal to 0.65438. So this tells me x, absolute value of x, must be less than or equal to this number. And that's what we were trying to find, the x values for a fourth degree Maclaurin with an error of that. So since this is an absolute value, what we have is it's actually negative 0.65438 is less than or equal to x is less than or equal to positive 0.65438. So those are the x values, any x between those two numbers. Okay. So, you know, the problems start out, the first example started out where you're always finding this error bound, this remainder, and then they kind of segue into, well, let's ask you to find the other parts. You will notice, though, in all these, this process of kind of finding a maximum for this derivative is a function that you know something about. Okay, that is it. Kind of a long video. Sorry about that.